Hello, here in this section, 6.7, we're going to look at something called common logarithms. Here's the why. We need the ability to solve for x when it is in the exponent or even in a log, or a logarithm. The reason this is helpful is it helps us estimate population size looking into the future. It helps us when investing and making decisions about how long to keep money in investment accounts. That's just two quick examples of where we would use exponential growth or decay. Other examples would be bacteria growth or endangered species and looking at their population growths. Anything that uses exponential growth or decay or models that we've seen, we're going to need the skills we learned today in order to solve for particular values. So let's get started. It says graph y1 is 6,000 and y2 as 4 to the 3x power in our calculator, and sketch the graph to the right. Now, I will say, after I went into y equals and typed those in, I went to the window button, which on the calculator, here's the screen. The window button is right next to y equals, right? So window button's right there. And I set my x minimum to 0. I kept my x max at 10. I set my y minimum to 0 and took my y max up to 7,000 so that I could see high enough. Right, and what I ended up getting was this. I'm just going to take it to 5 here. And then I'm going to count every other line as 1,000. All right. Well, we had a line, y equals 6,000, and it would look like this. It's going to be that horizontal line on your calculator. It stays flat forever. Now, the y2, which was 4 to the 3x power, takes a long time to get going, but then eventually it curves up and hits. So it looks like this, if I can get a good sketch. Doesn't shoot up right away, but then it shoots up like that. And the lines cross over. Now, it says, how can we use this information to solve an equation like this? 4 to the 3x power is equal to 6,000. Well, what's really going on here in our calculator, or anytime we're solving equations in general, what you're really looking for is the x-coordinate of this intersection point. So I need to know, where did they cross over in the x direction? And anytime you're solving an equation, that's actually what you're finding. You're finding where do the two curves cross, and what's that x-coordinate. So how can we use this information to do that? What we're going to use on our calculator is second trace, and then option 5 is intersect. And we've done this before, and if you're familiar with it, you can go through the process of hitting enter 3 times, right? And after you do that, you hit enter times 3. You would get an x-coordinate of where they would cross to be, I'm doing mine right now on the calculator, 2.09, approximately. So I'm going to change these equals into approximately. So what that would mean is that if we took 4 to the 3 times 2.09 power, we're expecting it to land near 6,000. And the more decimals you use, the more accurate your answer would be. And if we go up here and we do it, if I type that in on my calculator as 4 raised up to the 3 times 2.09 power, I actually get 5955.47. So we're a little bit off. But the more decimals that we'd use, the closer it would get to being 6,000. What we're going to learn today is how to just find that answer on our own without having to make graphs and using second trace intersect. So, let's take a look at this. Solving any equation graphically, which is what we just did, is solved by setting one side in y1 and the other side in y2 and finding their intersection. I do this on the math team all the time. They'll give me an equation where both sides are very complicated and I don't know how to solve it by hand, but if you can graph it, all you have to do is find out where they cross. So now let's look at this same equation but without a graph. It says, how could we solve 4 to the 3x power is equal to 6,000 by hand? Well, it says, well, what's stumping us right at the start? We know we want to use opposites, but x is in the exponent. So when x is in the exponent, we have to think, what is that opposite step to take? Here's what we can't do. I can't divide both sides by 4 because I have to take care of the exponent first. I can't even divide by 3 to get rid of that 3 because that 3 is in the exponent. So we're essentially stuck until we can figure out what do we need to do to fix the fact that x is up in the exponent area. What we're going to have to do is one of our old tricks. If x is in the exponent, so if x is an exponent, we're going to need to bring in drop, log, and roll from the other day, which is where the 4 drops down as the base, and the 3x and the 6,000 swap places. That's the opposite of x in the exponent. If x is in the exponent, drop, log, and roll is the opposite that helps get us down. And now, once we have x down, we are now able to divide both sides by 3. So our x is going to be equal to log base 4 of 6,000 divided by 3. So let's talk about how we can type that in on the calculator. If we have the newer calculators, what you're going to hit is you are going to hit alpha, right, which on the calculator, here's the screen, you have y equals, you have second, all right, so that button there is y equals. This button here is second. You are now going to hit alpha, and then you're going to hit window. And when you hit alpha window, option 5 is log base. We saw this the other day. And it will allow you to type in log base 4 of 6,000. So what you would then do is you'd hit those buttons, and it would give you this, and you'd fill in a 4 in that box there, a 6,000 there, and then you'd push divide by 3. And when you do that, what you'll notice is that you get the same answer that we had up above, which is approximately 2.09. If you have the old calculator, what you'll need to do is the change of base formula. So you'll need to do pushing the log button, which on a calculator is near the bottom. It's about halfway down. Right here it says log. You're going to type in log of 6,000 divided by log of 4. And then you're going to need to divide all that by 3. And a couple ways you could do that is to hit enter and then push divide by 3. You could also put all of that into parentheses and divide by 3 like that. If you did it correctly, you should get 2.09. So that's how we can solve these without graphs. And the explanation was a little long, but it normally happens this quickly, which is much faster than using a graph. So that's using drop, log, and roll. We can also solve going the opposite direction. What about when x is stuck in a logarithm? We need to know the base. If you don't see a base, it's an invisible 10. The other trick we used to use was loop and swoop. And what that'll look like is you take your base You raise it to that side, and then you set it equal to what's there. And then you solve like normal. 10 squared is 100. So when I add 3 to both sides and then divide by 4, I get that x is equal to 103 divided by 4. And we can check that very easily on the calculator by hitting the log button and then typing in this. And if you do that, so if you hit the log button and then do 4 times 103 divided by 4, subtract 3, you will get the answer of 2. And that's a little proof that you can double check your answers even when x is in a logarithm. Now you'll need to know how to do this because I highly doubt that anybody can look at this problem and tell me that the answer is 103 divided by 4 because it's a big messy decimal. So using these methods such as drop, log, and roll and loop and swoop from the other day will be very important to your success on this section. There can also be properties of logarithms that show up as well when we're trying to solve logarithmic equations. And so you have to be familiar with those rules as well. And what those rules were, if we had the same log, so the same base, so in this case they're both base 10, and we add them together, we could combine the inside parts with multiplication. So we essentially turn it into one log with multiplication because of the addition. And that was one of your properties of logarithms from a previous lesson. So really now here what I'm solving for is after I distribute on the inside x squared, and this should be a subtract, x squared minus 3x is equal to 1. Our base is 10, and this is another example of where we need to use loop and swoop. So we have 10 to the first power is equal to x squared minus 3x. And so this is now turned into a quadratic. We always want quadratics equal to 0, so I'm going to need to subtract 10 from both sides. And then our options to solve from this point moving forward would be quadratic formula, factoring, which is what the method I'm going to take. This would factor to x minus 5, x plus 2, and then we'd use the zero product property by setting up each piece equal to 0 and solving. So this would give us that x is equal to 5, and x is equal to a negative 2. Now, we found both of these answers, and we've been studying in the past, anytime an equation starts off as one thing, so this started off as a logarithm, and it ended up being quadratic, we knew that that meant that there could be some extraneous solutions. So what we'll need to do is we'll need to go back through and double check both of these using our calculator. So we're going to check if I plug in 5 for x, does it work out correctly? And if you type that into your calculator, it does in fact work out correctly. If you type that in, this whole left side becomes a 1. However, if you try the above problem and you plug in negative 2 and you try to do it on your calculator, you're actually going to get an error because negative 2 is extraneous. And the reason for this is because logarithmic graphs, if you remembered, looked like this. They had an asymptote right there on the y-axis. So when we plug in negative 2, which would be over here, it can't get there. That's why you get an error. The blue logarithmic curve will never make it to negative 2. So negative 2 isn't a valid solution in this case. Now, I just quickly did one of each type. I did one drop, log, and roll. We did one loop and swoop. We did one where we need to use properties of logarithms. We'll get lots and lots of practice on these because there's a variety of scenarios that can come up. But let's continue to make it through, and then we will get some chances moving forward to practice the different types of scenarios. Here's a word problem, and this one deals with the population of a school growing, or in this case decreasing, so exponential decay, 6% each year. And we're going to figure out in how many years will it have 100 students. And this is something that math is used for all the time. Estimating populations in a city or state or country. Schools will look at it to track enrollment. And we use logarithms to find all this out. So, what this is, we're actually going to set this up as exponential growth, or in this case, decay. So it says the population currently is 160 students. And what's happening is that we're losing 6% each year, which means our decay factor is 0.94. We're only keeping 94% of our population each year. And we'll just set x up to be number of years. And what they wanted us to figure out is when will it have 100 students? So we're not equal to a y in this case. We're equal to specifically 100. X is in the exponent. We're going to need to use drop, log, and roll. But before we do that, we'll first need to move this 160. And when we do that, we could simplify the other side. 100 divided by 160. If we were to simplify that as a fraction, what we would get is 5/8. X is in the exponent, so we're ready for a drop, log, and roll. So where we'll get log base 0.94, and then the 5/8 and x switch spots, or they roll. And that looks very confusing, but if you type that in on your calculator, what you'll end up getting for x is that x is equal to approximately 7.5. So what that means is in between, year 7 and year 8 of this school, they're expecting to get down to an enrollment of 100 students. And we could check this by plugging it back in to the original equation. And when we do that, so 160 times 0.94 raised up to the 0.75, you'll see that it lands us very close to 100. So this is a really powerful example of when we'll use logarithms to help us solve equations of population. There are methods of solving these without a calculator. We did it back in 6.2. And that method was, if x was in the exponent, we needed to get both sides expressed as the same base, to where 27 is 3 cubed. And then we set the exponents equal. That method does still work, but not all the time. And we could have also solved this one with logarithms by doing drop, log, and roll. Because log base 3 of 27 is just a 3. So anytime you see these that have the same base, you can certainly do it like that. You could try to solve this problem by expressing the 32 as 2 to the 5th. You could have attempted to solve this one by setting up 5 to the 3x is equal to 5 to the negative third, because that's what 1 over 125 is. This one could be expressed as this. So all these are accomplishable by a past method that we had seen. You can also use drop, log, and roll on these as well. And what you'll see ends up happening is that you get the same answer, because log base 2 of 32 is a 5. And 5 equaling 5x plus 1 is the same thing you would get when you set those exponents equal. So both methods work on some types of problems. However, we need the method that we learned today to help us cover scenarios like this. 4 to the x is equal to 5. And the reason we need it is because I can't express a 5 as the same base as the 4. The only way to solve this one is to use drop, log, and roll, to where in this case x is equal to log base 4 of 5. And we could type that in on the calculator. And when we do that, we would get x is equal to approximately 1.16, which should make sense because 4 to the first power is 4. 4 squared is 16. So if I needed 4 to some power to equal a 5, 5 is very close to 4, which is why this exponent is very close to 1. And we're going to get lots of practice. This video is just supposed to show you one of each type. That way you can be prepared as we move into other resources.